Okay, last week we started talking about Newton's laws of motion and forces, um, which is basically the topic of this entire unit. We're going to be elaborating on these concepts throughout this 6 weeks. So, starting with Newton's first law, everybody know the Newton's first law of motion. This is sometimes called the law of inertia. So what this says is that an object at rest will stay at rest unless acted upon by an unbalanced force. The same thing for an object in motion. An object in motion will stay in motion unless acted upon by an unbalanced force. So essentially, guys, what this law is saying is that all objects have a natural resistance to change. That's basically what inertia means, resistance to change. If an object in motion, and it's like if you take an object in space and you throw it, it's going to keep going on forever and ever and ever and ever without end. It's going to stay in motion. It's going to continue moving at a constant velocity. It's not going to be changing its direction, just moving at a constant velocity at a uniform speed forever, unless a force decides to come along and either changes its direction of motion or stops the object. The same thing for an object at rest. If an object is at rest, it's going to stay at rest forever until a force acts on it. So that's Newton's first law of motion. Of course, I posted an Edpuzzle video that gave you guys real-world examples of that. So be thinking of those examples as we go throughout this unit. Newton's second law of motion. I'm not going to say a whole lot about this law other than this is Newton's mathematical law, which is force is equal to mass times acceleration. Okay, F equals ma. So basically what this is saying is if you have objects and you want an object to accelerate, you'll just apply force on that object. And of course, if you know the object's mass, this equation tells you the magnitude of the acceleration. Okay, so that's Newton's second law. And lastly, Newton's third law. For every action, there's an equal and opposite reaction. So if I push on an object, that object pushes back on me. There's an equal and opposite reaction. That's Newton's third law. Okay. And of course, and again, I'm just briefly reviewing what we talked about last class period before we start talking about the normal force for the day. And of course, last class period, we worked out several problems. This problem right here, I want to remind you all what we did here. Well, because we're going to be using this concept today when it says, what is the weight of a 0.1 kilogram apple? So guys, what exactly is weight? I mentioned this last time. So remember I said, imagine that you're standing on a scale. If you're standing on a scale, that scale is able to tell you what your weight is. How does it do that? Well, think about what is happening on a scale. As you stand on a scale, obviously you are being pulled to the scale because there's a force of gravity that is pulling you and causing you to press up against the scale. So basically, guys, the scale is basically measuring the force of gravity indirectly. It's measuring the force of gravity indirectly. So in other words, if you want to know an object's weight, and again, I'm going to write this down because we're going to do this, we're going to use this today. If you want to know an object's weight, all you would need to do is just calculate the force of gravity acting on that object. Okay, because force of gravity will tell you the object's weight, right? Because the scale is indirectly measuring the force of gravity because the force is what's responsible for pulling the individual downward and causing that individual to press up against the scale. Okay, so force of gravity is equivalent to the object's weight. Now, if you guys remember, force of gravity, well, you know what? Let me not get too ahead of myself. If you guys remember Newton's second law, if you want to solve for force, it's just equal to an object's mass times that object's acceleration. But what about a specific force? So the specific force of gravity. So the force of gravity is equal to an object's mass times a specific acceleration. And does anybody remember the acceleration of gravity? That number that I gave you guys last week that I told you guys remember? The acceleration of gravity. Anybody remember that number? Remember what I said last week? If any object is falling toward the Earth, what is its rate of acceleration? Anyway? So if y'all remember, the acceleration of gravity was 9.8 meters per second squared. So that's an important constant I need for you all to remember. So basically, guys, if we want to calculate the weight of the apple here, and we need to solve for the force of gravity that is pulling the apple downward. So we're going to take 0.1 kilograms, which is the mass of the apple, and we're going to plug it into this equation. So force of gravity is equal to 0.1 times 9.8, which of course is equal to 0.98 newtons. Okay. And of course, 0.98 newtons is equal to the weight. 0.98 newtons is equal to the weight of your apple. Okay, so guys, just be sure you're following along what I did, because there will be problems like this on your homework assignment for today. Anytime you want to know an object's weight, it's just 0.1 times, it's just mass times 0.98. It's mass times 9.8, and in this case, the mass was 0.1 kilograms. Okay, because force of gravity is equal to an object's weight. Any questions there before we move on? Okay. All right, let me go ahead and clear this page. So that it'll be ready for my next class. By the way, guys, I want to say something here for your homework. Just something that I want to throw out here. Even though technically the equation for the force of gravity is equal to mass times 9.8. On your homework problems, to make things simple for your homework problems, we're just going to round 9.8 off to 10. Okay. So I would write that down, because that's the equation you're going to be using for your homework problems. Force of gravity is equal to mass times 10. Again, we're just rounding 9.8 out to 10 to make your calculations easier. Since 9.8 is so close to 10, we can basically just round it off to just give an estimate, a very close estimate for what the magnitude of the force of gravity is. So just something I want you guys to keep in mind, okay? All right. So now, moving on to what we're going to be talking about today. Okay. Today, we are going to focus on what is known as the normal force. Okay. What exactly is the normal force? By the way, we're going to be spending this week talking about types of forces. There are many types of forces in nature. There's friction, there's tension, there's various types of forces that exist. We've already talked about, we've already focused on one of those forces, and that's gravity. Gravity is a force you guys are very, very familiar with. Today, we're going to focus specifically on the normal force. What exactly is the normal force? Well, I'm going to tell you guys right now, normal just means, normal is just a math term that just means perpendicular. And that's what the normal force is. It's a perpendicular force that that is caused by two objects in contact with each other. So when one object presses against another object, there's a normal force between those two objects, which is perpendicular to the surface of contact. So let me give you an example of what I mean by that. So guys, notice what I have here. Okay. I have two books here. Okay. So one book is sitting on another. Okay. So guys, consider the blue book right here, guys. So the blue book is sitting on top of the white book. Okay. How many forces right now are acting on the blue book? Well, hopefully you guys guessed it that there are two forces acting on the blue book. Obviously, right now, there's the force of gravity acting on the blue book, and the force of gravity is pulling the blue book downward, right? Now, guys, if gravity is pulling the blue book downward, and that's the only thing that was happening, obviously you will see this book basically accelerating downward in this direction. It would appear to go through the white book. But obviously, that's not what's happening. In fact, if you notice, the blue book is just at rest. So there has to be something else going on here that is balancing gravity. If gravity is pulling the book downward, okay, there must be something else acting on the blue book. And guys, that something else is what we call the normal force. It turns out, since the blue book is pressing up against the white book itself is pushing upward on the blue book. Causing it to remain at rest. In other words, the force of the white book is balancing out. The force from the white book on the blue book is balancing out the force of gravity. Again, we call that force the normal force. Okay, so here's how we'll say this. So in addition to the force of gravity acting on the blue book, there's also a normal force from the white book pushing upward on the blue book. Okay, everybody got that? So the normal force arises from two objects in direct contact with each other. Okay, if one object presses against another object, the other object pushes back. So there's a normal force between those two objects, and that force is always perpendicular to the surface of contact. I'm gonna repeat that again because I want to be sure you guys get that in your heads. Okay, so there's a force of gravity right now acting on the blue book, which is pulling it downward. But in order for the blue book to be at rest, there has to be another force balancing that. That other force is the normal force. So the normal force is pushing upward on the blue book. So there's a normal force from the surface of the white book that is pushing upward on the blue book that is balancing gravity. And so since the blue book is at rest, in this case, the normal force must balance gravity. Okay. And briefly, I'm going to show you guys something. There is a 3-minute video that I'm going to post in Schoology from YouTube that really does a good job of explaining the normal force. Let me go ahead and show that to you guys right now.
Now we can consider.
Okay, let me get ready to share my screen. And again, these concepts will be on the homework assignment for this afternoon. Okay, I'm going to share my computer screen here. I'm going to share my sound. Hold on, let me. Okay. Make sure this is turned up. So guys, this 3-minute video here does a really good job of introducing the normal force to you all.
The normal force. Now we can consider the normal force. So our first question is, what do we mean by normal force? Let's start with one word at a time. Force, we've already talked about, is a push or pull on an object. So then we get to normal. Now what we don't mean by this is it's not an ordinary force. While they happen all the time, that's not the usage of the word normal we mean. Instead, we're talking about a mathematical definition of normal that refers to the perpendicular. So for example, if I have a surface, my normal force is always going to be at a 90-degree angle perpendicular straight out from that surface. And I use the F with a sub n as my symbol for it, both capital F and capital N. So here's some examples. Again, if I have a horizontal surface, my normal force might be straight up from that surface. If I have a vertical surface, my perpendicular is going to be, say, out to the left. And if I have a sloped surface, my normal force is still going to be perpendicular, but that means it's going to be off at an angle. Now, when do you have the normal force? Anytime you have solid surfaces in contact with each other. The normal force is the force that prevents those solid objects from going through each other. Now, from Newton's third law, we know that forces come in pairs. So let's understand that in terms of a normal force. The ground pushes up on the block with a normal force, but the block also pushes down on the ground. If I push on the wall to the right, the wall pushes back on me to the left. These are force pairs. I push on it, it pushes back on me. In both cases, I can't push through the wall and the wall doesn't push through me. Now, if I've got multiple surfaces, like I have in this example, I have to consider a normal force for each one of the points of contact. So, for example, up here at my hands, I have a normal force where I'm pushing on the wall and the wall is pushing back on my hands. In this case, my front foot is going to have a second normal force, where my foot pushes down on the floor and the floor pushes up on that front foot. And in the back foot, we have a third normal force. And again, it's a force pair where my foot pushes down on the floor and the floor pushes back up on my foot. If I have multiple objects, I need to consider the surfaces for each one of those objects. So here I've got two boxes sitting on top of each other, sitting on the floor. Well, there's a surface between the two boxes, and so the green box pushes up on the blue box, but the blue box is also pushing down on the green box. And there's a surface contact between the green box and the floor, so that the floor pushes up on the green box and the green box pushes down on the floor. When I go to do force diagrams, remember that I want to treat each object separately. So my blue box has a normal force upwards due to the green box, and my green box has two normal forces, one due to the floor and one due to the box sitting on top of it. Now don't forget, both of those boxes also have a force of gravity, assuming they're sitting here on Earth and not out in space. And so your full force diagram would have to take into account not just the normal forces, but any other forces that are on there as well. So that's your introduction to the normal force.
Okay, so stop sharing my screen here. So that was a really good video introducing the normal force. One of the things that I want to say that she mentioned in the video, which I think was a really, really good point. Guys, so normal force, if you notice, it arises from Newton's third law whenever two objects are in contact with each other. So guys, basically what that's saying is that, if the blue book pushes down on the white book, then according to Newton's third law, the white book must push up, must also push up on the blue book, right? There's an action-reaction pair. One object pushes on the other object pushes back. So just something to keep in mind. Okay. Something to keep in mind. Now, I'm going to spend the rest of my teaching time just working out examples that will look like the examples that you guys are going to see on your assignment for this afternoon. So let's do that. Okay, let me get ready to share my screen here. Okay. So, guys, we're gonna start off easy, and then we're gonna gradually move our way up to things that are more complicated. Okay. Imagine here that I have a blue box sitting on a table. Okay, so here's my blue box, and it's just sitting here on a table. And let us assume that the mass of the blue box is 3 kilograms. Okay. So the mass of our blue box is 3 kilograms. Now, the question is, what is the magnitude of the normal force right now acting on this blue box from the table? Obviously, there's a normal force from the table pushing up on the blue box to balance gravity because the blue box is just sitting there. It's at rest. It's not moving. So let me go ahead and draw those two forces that are acting on this diagram. So clearly there's a force of gravity pulling straight downward. So we have a force of gravity pulling straight downward. Okay. But in addition to the force of gravity, there's also a normal force from the table pushing up on this blue box. And I'm gonna do my best to draw these arrows roughly equal so that you guys can see that these forces are balanced. These forces have to be balanced because this box is not moving. It's not accelerating in any direction. Now, before we can find the magnitude of this normal force here, we need to first find the magnitude of the force of gravity here. And guys, y'all know how to find force of gravity. The force of gravity you guys know is force of gravity is equal to the object's mass times 10. Remember what I said in your problems here for your homework. You want to round 9.8 out to 10 to make your calculations easier. Okay, so what is the mass of this box here? This mass is 3 kilograms. So that means if the mass of the block is 3 kilograms, so the force of gravity here, 3 times 10 is just 30 newtons. Okay. So, guys, think logically here. If the force of gravity is 30 newtons pointed in the negative direction, that means the normal force must be 30 newtons pointed upward in the positive direction. So one's negative and the other's positive. And they have to be the same in order to balance. So the value of the normal force here is equal to 30 newtons. So in other words, guys, this right here represents the magnitude of the surface of this table here pushing up on this box. Okay? So that's an easy one. Let us do another one. Suppose I have a box here in red, and I know that the box is 7 kilograms. So I have a 7 kilogram box, and I want to know the magnitude of the normal force acting on this 7 kilogram block or box. So that's easy. Obviously, there's two forces acting on this block. There's gravity pulling it downward. So there's clearly gravity pulling it downward. So there's a gravitational force here pulling it downward. But there's also a normal force from the table pushing up. And again, those forces have to be equal and opposite because the red box isn't moving. It's at rest, it's accelerating, so those forces are balanced. So just to remind you guys, remember the equation for the force of gravity is equal to mass times 10. So if I know this mass here is 7 kilograms and 7 times 10 is 70 newtons, that means the magnitude of the force of gravity here is 70 newtons. Which means if the magnitude of the force of gravity is 70 newtons pointing in the negative direction, that means the magnitude of the normal force must be 70 newtons pointed in the positive direction. Okay. So those two forces have to balance. Okay. Any questions on that? Let us let us move on to something that is a little bit more complicated. I want you guys to think about this situation here. Imagine that I had a box sitting on a table, and while the box is already sitting on the table, someone comes along and they decide to push down on the box with the force. So they're pushing down on the box, and let's say the magnitude of this force is 10 newtons downward. Okay. Let me ask you guys a question before we. Oh, and by the way, I'm assuming the block is 5 kilograms. Okay. So this blue box here is 5 kilograms. So just imagine what's happening here, guys. There's a 5 kilogram box sitting on the table, and someone is pushing down on it. Let me ask you guys a question. If this block is sitting here and someone is pushing down on it, guys, what do you guys think would happen to the magnitude of the normal force here between these two surfaces as a result of someone pushing down on this object? Do you guys think the normal force will increase or decrease relative to its conditions? Well, relative to the condition if someone was not pushing down on it. So if someone wasn't pushing down on it, the normal force will be a certain value. But if someone comes along and pushes down on the box, what happens to the normal force? Does it increase or decrease? Exactly. Elijah said increase. You're exactly right, Elijah. And guys, that, by the way, that will be a question on the assignment later on. So that makes sense, guys. If this blue box, this blue book here is sitting on this white book, okay, if I push down on the blue book, okay, the act of me pushing down on the blue book causes the normal force between these surfaces to increase. Okay. If there was no force there, this normal force here would be 50 newtons. But I want you guys to see what the normal force is as a result of something pushing on it. So in order to do that, let me draw the other two forces just to give you an idea. Obviously, there's gravity acting on this object. And gravity acts straight downward. So there's gravity. And remember, guys, the equation for gravity is mass times 10. So if this mass here is 5 kilograms, 5 times 10 is 50 newtons. So the force of gravity here must be 50 newtons. Okay. Now, guys, the question is, what is the magnitude of this normal force? What is the magnitude of this normal force here? So, what is the magnitude of this normal force here? How do I know the magnitude of this force from, and again, I drew an up arrow to represent that the surface of this table is pushing up on this block here. So what is the magnitude of this normal force? Well, I'm going to give you guys a hint for how to solve for this. Because the object is at rest, our up forces should balance out our down forces. They should be balanced. Notice we have two down forces here and we have one up force. Right? Since we're not moving, these two down forces should balance this up force. So in other words, if you combine the two down forces, it's 10 newtons plus 50 newtons, which is equal to 60 newtons. So that means, guys, what that tells us is that this normal force here must have a magnitude of 60 newtons. Which Elijah, which just proves what you said. In other words, the normal force increase. Without someone pressing down on it, the normal force will be 50 newtons. But when someone comes along and press down on it, in this case, the normal force increased to 60 newtons. Okay. So let's work out another example like this so that whenever you guys see this on your assignment for this afternoon, you guys will be able to make sense of how to do this. Let us assume that we have a red box sitting on a table here. And this red box has a mass of 8 kilograms. And once again, the equation for the force of gravity is equal to mass times 10. Okay. Now, guys, imagine someone is pushing down on this surface. Let's say someone is pushing down on this surface with a force.
Hello?
Yes.
Can you put the attendance link in the chat?
Can someone put the attendance form in the chat for Simon? Because I'm right now in sharing mode.
Mm-hmm.
Can someone do that for Simon? Yes.
I have one more question.
Yes.
We staying here for the whole hour and 42 minutes or so?
No, just as long as I'm lecturing. But as soon as I'm done, you can get started on your assignment.
Okay.
Yeah. And as soon as I'm done with these example problems, I'm gonna let you guys know when I'm gonna let you go. Okay. So guys, so imagine you have a situation like this where you have an 8 kilogram block and you have a 20 Newton force pushing down on it. Okay. And the problem asks you to solve for the magnitude of the normal force acting on your surface. So guys, on your homework problems, whenever you guys are given pictures like this, you want to look at it, and then the next thing you want to do, you want to draw the other two forces acting on the object, that is gravity and the normal force. And then using that information, you can actually calculate the magnitude of the normal force. So let's go ahead and do that now. If a block, a red block, has a 20 Newton force pushing down on it, what are the other two forces here? There's gravity. So let me draw my wrong color. Let me draw my gravitational force here. So and then there's also a normal force because the surface of this table is pushing up on the block in red. Now, what is the magnitude of the force of gravity? If this is an 8 kilogram block, 8 times 10 is 80 newtons. Okay. So if this block here is 80 newtons, the question is, what is the magnitude of this normal force? Remember what I said, guys. If the block is not moving, if it's at rest, remember all the forces should be in balance, meaning the two down arrows should balance the up arrow. So in this case right here, if I add up my two down forces, yeah, 20 plus 80, exactly, Elijah, gives you 100. So that means the magnitude of this normal force here is 100 newtons. Okay. So I think you guys get an idea how to work out these problems. Yeah. But now, Elijah, let me ask you another question. Okay, you just told me that if I push down on a surface, the normal force increases. But let me ask you a question. What if I have two objects, and instead of pushing down on the blue book, what if I slightly pull up on the blue book? So if I slightly pull up on this object, what happens to the normal force between the two surfaces in that case if I pull up instead of pushing down? What do you think would happen in that case? The normal force decreases. Exactly. So guys, these are common answers that you guys are going to see on the assignment today. And guys, let us work out one example like that. So imagine that I have a 15 kilogram block, okay, and I have a 25 Newton force. I have a 25 Newton force pulling up on it. So let me draw my force. So this force here is 25 newtons. Okay. So the question is, what in this particular situation right here, what is the magnitude of the normal force between these two surfaces? Okay, so in order to do that, let us go ahead and draw our other two forces on our object. So there's always the force of gravity acting straight down. So there's gravity acting straight down. And if this is a 15 kilogram block, 15 times 10 gives me 150. So the magnitude of the force of gravity here is 150 newtons. Okay. Now the question is, what is the magnitude of this normal force pushing up on this surface? Okay. What is the magnitude of this normal force pushing up on this surface? Well, guys, remember what I said. Since the object is not accelerating, it's not moving, all of our up forces should balance our down force. And you're exactly right, Elijah. It is 125 newtons. And how did you know that? Because if this arrow here is 150, then that means this arrow plus this arrow added together must equal 150. So this right here must be 100. So it must be 125 newtons. Okay, because these two up arrows have to balance the one down arrow. And sorry guys, I didn't draw these arrows to scale. That's my fault. But just know that, because this arrow should actually be smaller than that. But you guys get the point. But 25 plus 125 is equal to 150. These forces must be balanced. And of course, you know what? Let me go ahead and make this arrow a little bit smaller, just to be sure that I'm. There you go. Because these two arrows added together should be equal to this. Even that's not entirely perfect, but you guys get the idea. Okay. So on the assignment for today, there will be various situations. Let me pull this. Give me just a second while I pull up one of these worksheets. Hold on, guys. Let me. Okay, sorry guys, I was kind of clearing the screen on this PDF file, but let me go ahead and share my screen now that I have this cleared. Okay, so guys, I want to close the day looking at a few examples, just to be sure everybody's clear on how to correctly draw their normal force. So look at this situation here where it says, where we have various illustrations here. It says, let's meet Jim. He's very slim. Draw and label all the forces acting on Slim Jim. Okay, so guys, I want to say something here. Whenever you guys are drawing your assignment, whenever you guys are doing your assignment and you're drawing normal forces, or you're making sure that your normal forces are drawn correctly, you want to pay very careful attention to what the object is. So in this case, it says draw all the forces acting on Jim. Now, guys, I could give you an example where I say draw all the normal forces acting on the wall, or all the normal forces acting on the floor. but it's in this case it says what are the forces acting on Jim. So remember, guys, in order to know where your normal force is, you want to look for your surfaces of contact. Notice there's two surfaces of contact here because it says Jim is leaning against the wall with 1 foot up. So there's a surface of contact here, and then there's also a surface of contact here. So that means this object here should have two normal forces acting on Jim. Okay, so clearly, there's a normal force here acting on Jim. And guys, be sure your arrow is pointed in the correct direction. Hey guys, I'm sorry about that. For some reason, I don't know why the Zoom call just disappeared. Like, well, the app went blank and it came back up. I don't know why. What the Zoom out? It just basically just cut off and it switched back on. Can everybody hear me? Okay. Now I don't know why that happened. Can y'all hear me? Again, I don't know what you guys saw from y'all's end, but from my end, like I said, the Zoom call it just cut off and it came back on. That was really, really weird. Anyway, let me share my screen because I want to hurry up and finish this up. Finish this so I can give you guys the opportunity to work on your assignment before class ends. Okay. So I want to say this. Hold on. Okay. So we have two normal forces acting on Jim here. There's the wall itself pushing up against Jim. And that makes sense, guys. That's Newton's third law. That should be obvious. If Jim pushes against the wall by definition has to push back against Jim. Right? That's for every action, there's an equal and opposite reaction. What about the normal force here? Where's the normal force pointed here? The normal force here is pointed straight up. And that makes sense, right? Because if Jim's foot pushes down on the floor, then the floor pushes back up on Jim. Because, again, we're concerned with the forces acting on Jim. Okay? So, again, I'm not asking for the forces acting on the floor, the forces acting on the wall. I'm asking for the normal forces acting on Jim. So, let us look at B, guys. If Jim leans against the wall with both feet on the ground, how many normal forces do we have here acting on Jim? Well, notice there's three surfaces of contact, so there's three normal forces. So there's a normal force acting here. Try my best to draw these arrows. There's a normal force acting here. And then there's a normal force acting here. Okay. Looking at this illustration here. Now, in this case, Jim is standing on a table and he's pushing on the ceiling like this. So how many normal forces here do we have acting on Jim? Well, if you notice, there's four surfaces of contact here. There's a contact with this surface here. There's a contact with this surface. There's a contact with this surface. And there's a contact with this surface. That means there should be four normal forces here acting on Jim. So, guys, we know, guys, if Jim pushes on the table, according to his third law, the table pushes back up on Jim. So here, our force points straight up like this. So that's a force. And here, there's also a force like this. Okay. But guys, what about the arrows here? In what direction is the normal force here from the ceiling pushing on Jim? Where do those arrows point to. Remember, guys, if he pushes up on the ceiling, according to the third law, the ceiling must be pushing back on him because we're looking for the forces acting on Jim. Jim is our object here. So there's a force from the ceiling pushing down on him here. Again, that's the surface of contact. And then there's another force acting here because this is another surface of contact. Okay. So hopefully that gives you guys an idea of how to draw your normal forces in the correct directions. Almost done here. I'm just going to go over a few more things here. Number 2 says, if a surface has to support more, it has to provide more normal force. Does the following increase or decrease the normal force? So we already talked about this here. If you have an object sitting on another surface and you push down on that object, then that obviously increases the magnitude of the normal force between those two surfaces. So for number 2, I'm going to put I for increase. So just thinking logically here. Guys, what do you think on number 2? If you have an object sitting on top of some surface and you sit another object on top of it, what does that do to the normal force? Does that increase it or decrease it? That should be obvious. You're sitting one object on top of the other. So in that situation, the normal force should increase. What about this? What about friction? So imagine, guys, that I have two objects. And you guys see this blue book here. This blue book slides across the surface of this white book. So there's clearly friction between those two surfaces. But if you guys notice, guys, friction is a horizontal force. It's not a vertical force in this situation. So in other words, friction does nothing to the normal force. In this case, the friction has no impact on the normal force. So in other words, I'm going to put in there for nothing. So it says, does the following increase or decrease normal force? I'm going to put in for nothing, that nothing happens. Or in other words, I'm going to put, it's negligible. Well, not negligible, but nothing happens as a result. Nothing happens to the normal force as a result of friction acting between the two surfaces. What about decreasing the weight of the object sitting on the surface? That should be obvious. If you decrease the weight of the object, you decrease the normal force, right? Because obviously there's less. Basically if there's less weight, that means there's less gravity pulling down. So we've already talked about this. What if you pull up on the object? So if you have an object, you pull up on it. We also say that decreases the normal force. Increasing the weight of an object, that's obvious. If you increase the weight of an object sitting on a surface, then you increase the normal force acting between the surfaces of those two objects. What about pushing on the object sideways? Well, that's a horizontal force. So the horizontal forces have no impact on the vertical forces in that case. So that would be nothing would happen in that case. What about pushing down on an object at an angle? Even though you're pushing at an angle, you're still pushing down. So the act of pushing down still increases the normal force. Okay. Okay, guys, I'm gonna spend about like 3 more minutes. I'm gonna try to have you guys working on your assignment by the time 8:30 gets here. But one of the things that I want to look at here is that looking at number 4, okay. On number 4, we have a diagram of a roller coaster here, and if we're asked to draw the magnitude of the normal force at various points, how will we do that? So, guys, remember what we said at the beginning of this lecture. The normal force is always perpendicular to the surface of contact. So, if you kind of zoom in here, on this region right here, you notice where the surface of contact is between the roller coaster and the surface of the track. So that means the normal force must be perpendicular to that surface, which means the normal force in this case must be pointing like this at an angle, perpendicular to that surface, right? Because the track itself pushes on the roller coaster. What about the normal force here? Well, this is obvious. If you look at this surface of contact, the surface of contact between the roller coaster and the track is here. So that means here in this particular example, the normal force pushes straight up, because in that case, the surface of the track pushes up on the roller coaster itself. Okay, because the normal force is always perpendicular to the surface of contact. And the same thing here for situation C. The normal force pushes straight up on the roller coaster because it's perpendicular between the surfaces of contact. Okay, because the roller coaster is in direct contact with the track. So you always draw a normal force where you have surfaces of contact. Okay. All right, it's 8:30. So before I let you guys go, I want to say this: as on your homework, whenever you're doing your homework, like whenever you guys are working on your homework, and it gives you various diagrams that look like this, remember what you want to do first. You want to draw the other two forces on the diagram. So, for instance, there's gravity acting here, and there's also the normal force. And then once you draw those two forces, you can just use simple math to make sure that all your up forces balance out with your down forces in order to solve for the magnitude of the normal force. Okay, so just keep that in mind. Are there any questions for me before I let you guys go? Okay, guys, give me about 5 minutes. In about 5 minutes, I'm going to have the everything posted in Schoology. First period ends at 9:11, which is plenty of time for you guys to get the assignment done. Once I get it posted, because it's just a few multiple choice questions. So we have 40 more minutes left in class. Also, guys, even though I'm gonna let you all go, I'm gonna keep the Zoom call open. So in case you guys if you want to stay on, you're free to do so. If you want to sign out, you're free to do so. If you want to log back in and ask me a question, you can do that as well. Again, I'm going to keep the Zoom call open until 9:11. If there are no immediate questions for me, you guys are free to go. All right, have a good rest of your morning. Bye, guys.